Jumping spiders are one of the most visually sophisticated predators alive today. These extraordinary hunters are the largest family of spiders on Earth, beaten only by sheet-web spiders in total species count. More than 6,000 species are recognized, meaning they make up over 13% of all known spider species. Jumping spiders are also one of only 2 lineages of arachnids to have evolved camera-type eyes with movable retinas, allowing them visual acuity that rivals many vertebrates. What makes some jumping spiders truly extraordinary, however, is that they don't react to prey movement. They anticipate it, striking where the prey will be rather than where it is. Jumping spiders, known scientifically as Salticidae, from the Latin for dancing or leaping, have some amazingly diverse hunting strategies, with species that mimic ants, stalk prey like cats, and even hunt other jumping spiders. They're found on every continent except for Antarctica. Unlike web-building orb weavers and funnel web spiders, jumping spiders hunt actively using vision rather than vibration detection. They possess enormous forward-facing principal eyes that can move internally, whereas other spiders have fixed eye arrangements. Despite their astonishing modern diversity, the origin of jumping spiders' predictive hunting abilities is still poorly understood. The early evolution of this spectacular cognitive capability is one of the most intriguing mysteries in arachnology. For starters, what exactly makes jumping spider hunting so remarkably sophisticated? Well, that brings us to the first fascinating aspect of Salticidae neurological capability. The most striking feature of jumping spiders is their ability to calculate future prey positions before executing jumps. This hunter is equipped with a visual processing system that allows it to predict trajectory, velocity, and interception points in real time. While jumping spiders are not giants in absolute size, species like Portia and Phidippus are giants relative to other salticids, reaching body lengths of up to 22 millimeters, enormous for visually hunting spiders. Portia fimbriata possesses neural circuits dedicated specifically to motion prediction and spatial calculation. These are just stunning adaptations. It's clear that this animal is perfectly designed for anticipatory hunting. The principal eyes contain a unique 4-layered retina. The deepest layer is specifically tuned to detect green wavelengths. These eyes work like telephoto lenses, with incredible resolution that allows them to distinguish prey details at distances of 30 to 40 centimeters. Portia species are definitely capable of complex predictive calculations, with enlarged brains and all the right neural architecture. However, the key difference is that this cognitive processing happens in a brain smaller than a poppy seed. It weighs less than a milligram, yet contains roughly 600,000 neurons. Predictive motion tracking is a biological superpower. By analyzing velocity vectors and acceleration patterns of moving prey, jumping spiders can calculate interception coordinates. They then execute jumps to where the target will be rather than where it currently is. Jumping spiders that use anticipatory hunting possess relatively large anterior lateral eyes. These are part of the secondary visual system involved in detecting motion and triggering pursuit responses. Research published in 2012 by the University of Canterbury showed that Portia species could plan detours up to an hour long to reach prey. This discovery helped explain how jumping spiders evolved such remarkable cognitive abilities, despite having brains that are orders of magnitude smaller than vertebrates. The hunting sequence involves multiple calculation phases. First, the spider detects motion using its secondary eyes. Then it rotates its body to bring the principal eyes to bear on the target. Studies using high-speed cameras have revealed something fascinating. Successful jumps to intercept moving prey require the spider to lead its target. The spider calculates angles that account for both prey speed and its own jump velocity, which can reach 30 body lengths per second. Looking at the prey species that jumping spiders hunt, this shows us how predictive capability relates to survival pressure. It helps solve questions that salticid researchers had been debating for decades. The evolution of anticipatory hunting didn't occur in a vacuum. It developed as prey species became faster, more erratic, and more alert to predator threats. Flies, which constitute a major portion of jumping spider diet, can detect approaching threats remarkably quickly. They execute escape maneuvers in as little as 50 milliseconds. This presents an enormous challenge. By the time a spider launches toward where a fly currently is, that fly will have departed. Now, I need to quickly add here that modern fruit flies offer insight into how exactly evasive behavior works. Some fruit fly species retain basic escape responses. Others have evolved sophisticated threat assessment that evaluates approach angle and velocity. It therefore seems that jumping spiders use their predictive calculations to launch attacks from angles that minimize fly reaction time. They often approach from below or behind where the fly's visual field has blind spots. So it's clear that jumping spiders have developed remarkable diversity in prey handling strategies beyond simple prediction. These hunters must have undergone significant cognitive adaptation. This makes sense as it would have coincided with the Cretaceous diversification of flying insects roughly 100 million years ago. But what about related species? Wolf spiders show us interesting parallels. While jumping spiders use vision-based prediction, wolf spiders have evolved vibration-based anticipation. This demonstrates how evolution can solve similar problems in different ways. Wolf spiders detect substrate vibrations and can calculate prey approach trajectories based on vibration patterns, though with far less precision. These spiders are found across every terrestrial habitat, from Australian deserts to Ecuadorian cloud forests. A 2018 study examining 342 different jumping spider species found that eye size correlates directly with habitat light levels and typical prey speed. This research, conducted by Cornell University researchers, revealed that species hunting in bright environments with fast-moving prey possessed significantly larger principal eyes. They also demonstrated more sophisticated predictive capabilities. Species like Phidippus audax, the bold jumping spider common across North America, can successfully intercept prey moving at speeds exceeding 50 centimeters per second. Laboratory experiments have shown these spiders catching houseflies in mid-flight. This requires calculations that account for three-dimensional trajectories and the mechanical limitations of their own jumping apparatus. It's at this point that we must look at how modern jumping spiders are classified. This helps us make better sense of these animals and their extraordinary capabilities. The relationship of Salticidae to other spider families has long been debated. They were previously positioned as relatives of lynx spiders and wolf spiders based on hunting behavior. Recent research has found better genetic support for their position within the RTA clade, grouping them with ground spiders and sac spiders. The classification of jumping spiders splits them into major groups. The Salticidae includes most familiar jumping spiders with typical body forms. Several basal subfamilies like Lissomaninae retain more primitive features. The Salticidae include familiar genera like Phidippus, Salticus, and Portia. Basal groups include the ant-mimicking spiders of Southeast Asia. The recent discovery of Cretacenica from Burmese amber has been key to understanding Salticid evolution. Dating to 99 million years ago, this ancient jumping spider shows clear evidence of enlarged anterior median eyes. It was found to be closely related to modern Spartainae, suggesting that sophisticated vision evolved very early in jumping spider history. As a quick aside, a 2021 study looking at 600 different species investigated how they relate to modern lineages. According to this study, anticipatory prey interception capabilities evolved independently at least 3 times within Salticidae. This suggests strong selective pressure from increasingly evasive prey. The study also found that brain size relative to body mass increased significantly in lineages that specialized in hunting flying insects. Anyway, going back to current understanding, jumping spiders show remarkable visual sophistication unmatched among invertebrates. They have evolved cognitive predictive capabilities previously thought to require vertebrate-level brains. They are classified into multiple groups based on eye arrangements and hunting strategies. So, jumping spiders are remarkable arachnids that have evolved predictive hunting capabilities. These allow them to intercept prey by calculating future positions. From their movable retina tubes to their sophisticated neural processing, these animals represent one of nature's most successful solutions. They solve the challenge of hunting fast-moving prey with minimal sensory and processing hardware. The fact that a brain smaller than a grain of sand can perform calculations that predict three-dimensional trajectories demonstrates something profound. Cognitive sophistication doesn't require large brains, just efficient ones. Today, jumping spiders can be found in virtually every terrestrial ecosystem. They continue to hunt using vision-based prediction that puts many larger predators to shame. Understanding these hunters helps us appreciate how evolution can produce complex cognition through unexpected pathways. Recent research has revealed that jumping spiders may possess attention mechanisms, working memory, and even REM-like sleep states. Questions remain about the subjective experience of these animals and the ultimate limits of miniaturized cognition. There's clearly still much to be learned about jumping spider neurobiology and cognition. But there's no doubt that this fascinating family of spiders represents an astonishing example of evolutionary innovation. Future studies will likely uncover even more fascinating details about how these animals process visual information and make split-second decisions. If you enjoyed this deep dive into spider cognition, let me know what other remarkable animals you'd like to explore next. Please like this video and subscribe to the channel if you enjoyed it. And be sure to press that bell icon so you can learn more about our world and the wonderful life that surrounds us all.